What up? It's linear algebra. All right, one flashcard, dude. What do we got? What does it mean to say a linear system is consistent? A linear system is said to be consistent if it has at least one solution. All right, what did we learn about yesterday? Were we learning about inverses? I think that was the day before, right? I remember we started the... Okay. Yeah, properties of inverses as well as powers of matrices. So properties of inverses, what do we got? I don't remember, but powers of matrices. So if a matrix is a square, we can say that it has exponent, like power, values of non-negative integers going to be equal to, essentially, what would that be equal to? Basically a times a times a times a, as many times as the power is, as many times as the number in the exponent is. How about for non-negative exponents? Or how about for negative exponents? For negative integer exponents, we've got, essentially, it's going to be equal to the inverse of a, parenthesis n, or to the power of n. All right. There's something along the lines of k times a is invertible, and the inverse is k to the negative 1, a to the negative 1. The inverse is invertible. Is it saying that a to the power of n is also invertible and a to the negative power of n is invertible? Something along those lines. I don't remember how that ties in. That was probably properties of inverses. Maybe? A property of inverse. So if two invertible matrices are multiplied together, then the product is invertible, and it can be found by basically it's like the product of the inverses reversed. What else do we learn about properties of inverses? That was one. Somewhere we learned that essentially arithmetic, two of the exponent rules, where like if you have a base to the exponent times the base to this an exponent, so the same bases, you can say it's the base to the exponent plus the other exponent. That works for matrices. Also, if you got a base to an exponent in parentheses times another exponent, then you can say it's the base to the power of the first exponent times the second exponent. That's true for matrices as well. Other than that, I'm not sure what else. I'm gonna have to check out what we got in the textbook. All right, it's looking like we forgot probably a lot of stuff. There's a lot of writing. What do we got? Okay. If a is invertible and it's an n is a non-negative integer, then the inverse of a is invertible. A to the n is invertible, and k times a is invertible. So if a is invertible and n is a non-negative integer. Okay, that's where that came from. That's in powers of a matrix. What did we say? Did we get that? Not quite, but kind of. No, we didn't get the if. The if a is invertible and n is a non-negative integer. Okay, then we got these exponent rules. Gosh, I'm trying to sit. Kind of like, ow. Kind of like this. All right, that's fine, I guess. If a matrix is invertible, negative n. Okay, yeah. Okay, that was right. Okay. A to the 0 is going to be the identity matrix. Okay, I forgot that. All right. Okay, determinant. The determinant of a 2x2 matrix is essentially the product of the two entries in the main diagonal minus the product of the entries not in the diagonal. And that, if the determinant is not equal to 0, then the matrix is invertible. And to find the matrix, we can use the formula, essentially 1 over the determinant times the matrix, but it's reordered from A, B, C, D to D, negative C, negative B, A. All right. All right. And I think that's everything I got to. I think that's everything from yesterday. Yeah. So we're gonna keep reading. Where was I? Where did I leave off here? All right, we're gonna keep reading, and then I'll be back to recall in a bit. We finished reading 1.4. All right, what do we read about? I know we read about properties of a transpose. That was the last section we read about. What else? What did we end up talking about last? That was powers. Powers of matrix. So we finished powers of matrix, and then there was one more in between. What did we read about powers of a matrix? Anything new? All right, properties of a transpose. Let's just do that right now then, I guess. Polynomials. Matrix polynomials. All right, matrix polynomials, these are pretty simple. To find P of the matrix, or the function, or the polynomial of the matrix, you're going to substitute the matrix in for all the variables, and then you're also going to multiply the constant by I, the identity matrix. Okay, here we go. Here's something. There was some note about in that powers of a matrix, I think, section. It was like, two matrices of the same base to do different powers, they're invertible. And you can draw from that the conclusion that two polynomials of the same matrix in the same matrix are also invertible. Properties of a transpose. So the transpose of a transpose is the original matrix. You can distribute it. So the transpose of A plus B is the same as the transpose of A plus the transpose of B. The same holds for subtraction. Also for multiplication. So A times B, the transpose of A times B is the same transpose as the transpose of A, or same result as the transpose of A times the transpose of B. And then the transpose of a scalar times a matrix, the same as the scalar times the transpose of the matrix. All right. If a matrix is invertible, then its transpose is also invertible. All right, only thing from the powers of a matrix that I forgot is, so typically in arithmetic, in real arithmetic, you've got, within parentheses, you got a plus b, and you got to the power of 2. That's the same as a squared plus 2ab plus b squared. That's not the same for matrix because matrices don't commute. So matrix multiplication doesn't commute. So the best we can say is a squared plus ab plus ba plus b squared equals the power, or a plus b to the power of 2. Except if the two matrices commute, then you can say, you know, in parentheses a plus b, matrix a plus b, both to the power of 2 equals a squared plus 2ab plus b squared. That's if they commute. But otherwise, no, you can't say that. All right. Wow. There you have it. We finished reading section 1.4. This is getting more complex, more abstract, a lot more proofs. So we'll see how we do. Yeah, there's a ton of working with proofs in this. We'll see how we do in the exercises. So lots to learn out of this section still. I'll talk to you tomorrow. See you.